So we start now, and it's my pleasure to introduce Konrad Zdanowski, who will talk to us from Warsaw about truth predicate for delta zero formulas and PSPACE. And I just want to thank Konrad for agreeing to do that. This is the last seminar for this season. After that, we will take a break until the end of January. So I will be sending emails about the program and what we're going to do. And if anyone is interested in giving a talk, please email me in the meantime, and we'll be making a schedule for the next semester. So welcome, Konrad.
Yes. So in the first place, let me thank you for the invitation and for the agreement to give a talk. And I will talk about the complexity of the truth predicate in weak arithmetics and about the complexity class PSPACE. And this will be more or less about how much of PSPACE we can reconstruct in a weak arithmetic. But motivations for this talk are more or less like that. First question, which is a kind of very big question in bounded arithmetic theory, is how we can define truth predicate for bounded formulas. And it seems that the only way we can do this in a classical setting is just to add to the weak arithmetic exponentiation function. So if we consider arithmetic with induction only for bounded formulas, and in Peano, let's say in Peano language, then there is a question how then we cannot prove totality of any function which grows above polynomial. So the way we can deal with that is, for example, to add some functions which are like exponentiation function or some sub-exponential function and state its totality as an axiom, like here in the first point. And we can ask what fast growing function do we need to define truth predicate for delta zero formulas? And exponentiation function is the only function which allows us to define truth predicate. We cannot do this with any functions of lower rate of growth. And on the other hand, it's clearly overshoot because it gives us too much power in order to define truth predicate for delta zero formulas. It gives us all elementary functions. So so it is a long-standing open problem, and there were different approaches to that. So, for example, an old PhD by Lesson tried to formulate in a way what does it mean that exponentiation function is really necessary to define a truth predicate. So, so the statement here is telling something like that. If we have a delta zero formula psi in a model which satisfies only I delta zero, so it does not need to satisfy totality of exponentiation, then and if we consider an element A and we want to check what is the delta zero truth about A, then there is no psi such that this psi describes delta zero truth about A. All delta zero properties of an element A, if we take as a parameter in the psi something which is not greater than 2 to the A to the big N, so to the omega indeed, essentially. So if this psi, which is also again a delta zero formula, has parameter which is not as big as 2 to A to non-standard to standard numbers, then psi cannot code a full delta zero truth about an element A. So and lesson showed that if we choose parameter above this, then there is such a psi, and indeed we can more or less easily write such a psi for which parameter of this size is enough. So this is one way of stating that exponentiation function is really needed, is necessary to define truth predicate for delta zero formulas.
Konrad, this is still introduction, but can you perhaps say a few words about how this phi is made from psi?
I will how psi is made, or how
phi is made given psi.
Given psi. No. It's not that phi is made in a way. Phi. Okay, so I have psi and I want to. It's not. It's a hypothesis. I mean, we don't know whether it is true. So maybe Lessan's conjecture is false simply, and there is such a psi.
I see. Right. So this is just a statement that you'll be right. Okay.
Yes. Okay, yes. So this is a statement which is not proven. Yes, of course. Thank you.
Right. Thank you.
So and we don't know really whether it is true or not, but it expresses in a way that that an iteration of exponentiation function. So this bound 2 to the a to standard numbers is just slightly above 2 to the a. And it seems it is needed to define the delta zero truth about a. But it is open problem whether it is really needed. And moreover, indeed, when we see some model theoretic constructions which are made for I delta zero plus exp, very often this exp is used only to define a truth predicate for delta zero formulas. And when we deal with end extension or some other construction, we offer state that we work with I delta zero plus exp, but exp is used just for define truth predicate for delta zero formulas, and then to do some construction uniformly. So very often what we really need is truth predicate, not exp itself. And also often we can, or maybe not so often, but we can, like in the second point, we have a results which rely exactly on the properties of truth predicate. So in the second point, I mentioned that we have a proof of consistency of this theory, which is also an open problem, and this proof relies either that we have a truth predicate for without exp or with negation of exp, or assuming that exp is really necessary, assuming Lessan's conjecture. So these are, in a sense, these are two very different assumptions, either that we do not need exp or that we do need exp to define this truth predicate. And under both of these assignments, we can show consistency of this theory, which is also a long-standing open problem. So so indeed, this play between exp and truth predicates, one can meet it in various situations. So what I wanted to do, it's quite natural, and we do this quite often, but we revert a problem. So we say, let's add truth predicate to the weak arithmetic, and let's see what we get in exchange. So of course, set of true delta zero sentences is PSPACE complete. So in a real world, we get simply in a way definition of PSPACE computations, and we will see how to do this. And then asking whether we can define set of true delta zero sentences without x, but with some sub-exponential function, is more or less a question whether whether PSPACE is contained in some sub-exponential complexity class, like alternating time for the class given by this sub-exponential function f, like omega1, or we will see such function. So I wanted to revert the problem, but when we add truth predicate to the weak arithmetic, first of all, we need to axiomatize it, and then we need to check whether the weakness of arithmetic allows us to get from truth predicate its full complexity. So okay, so the playground is like that. I mean, we have indeed two arithmetics. First will be the arithmetic that we work in. So and this will be the usual basis bounded arithmetic. So it differs from Peano arithmetic mainly in extension of the language. So maybe the most important thing is this function omega1, which is of sub-exponential growth, x to the logarithm of x. And of course, this changes the notion of bounded quantifiers because t may be using omega1 function. So usually we have also sharply bounded quantifiers, x less than logarithm of t, and we will have sigma b1 formulas and sigma b2 and so on, where we count alternations of bounded quantifiers, but bounded in a sense of our new language, of course. So with bounding terms with omega1. And this is arithmetic we work with, and we extend this arithmetic with truth predicate, and we have the whole hierarchy of this arithmetics. I will be interested in arithmetic with the induction for the full bounded language. So induction for all bounded formulas. But also it will be interesting for us when this psi in the induction axiom is sigma b1. So it is just existential bounded formula, because that will be an amount of induction that we want for truth predicate, for formulas with truth predicate. And such an arithmetic with sigma b1 induction corresponds to p-time computations. And the full such arithmetic, I mean, full with induction for all bounded formulas corresponds more or less to polynomial time hierarchy. So I want to have the full S2 plus a small amount of induction for truth predicate. We will see in a moment how it will be. And then we have truth predicate. So we need to say for which language we have truth predicate. And then for the truth predicate, I restrict the language to just to the Peano language, because what is important is that I will consider delta zero sentences in the Peano language, bounded sentences with bounds being just either variables or constants. Why is it so? More or less, it's because when we have, for example, non-standard formulas, and we allow bounds as arbitrary terms, then our bounds may grow very high. For example, when we iterate squaring function in our bounded quantifiers sequence, then we can get exponential bounds at the end. So, and it is important to keep control on the size of the model to which a formula refers. So I simply chose that I allow only the only bounds I allow are by variables and constants. It makes this delta zero class a bit weaker, of course, but the weaker this class is, the better, in a sense, when you want to say that it is still a powerful predicate, and it make the work with this predicate and control over this predicate much better. And with respect to semantics, we do not lose nothing, because we can always replace polynomial bounds with bounds with just variables and constants. So now let's think, what is a good truth predicate? So of course it should agree with quantifier-free sentences or formulas, and this is the first point. But and we have indeed easily, you can write an arithmetical formula which defines truth for quantifier-free formulas. So this is just an arithmetical axiom that truth predicates agrees on quantifier-free sentences. Then we should preserve Tarski conditions for Boolean connectives and for bounded quantification. So this is also expressible in arithmetical language easily. Of course, we have new predicate. TR is a new predicate, and here this Y should be deleted from TR. We have just one variable X under TR, and this X will be just a sentence, a delta zero sentence. And in the end, I assumed induction for sigma B1, polynomial induction for sigma B1 formulas with this predicate. So we have weak class of formulas, and this amount of induction for this indeed allows us to represent more or less p time with oracle being predicate TR, truth predicate. So it is just p time with truth predicate as an oracle.
So what is val t in the condition for delta zero? I'm just trying to read that. The truth.
Okay. This TRQ3.
No, below that.
Okay, so Q3 is,
yeah, the conditions for bounded quantifiers. I just, what is val or what is t?
Okay, so so t has to be a constant here, because we allow only constants, and this val of t is simply an element, a function which gives a value of a constant. So for example, it depends. Okay, so because this value of t is outside truth predicate, so on the left hand side, we have it under truth predicate, and then when we take it outside, we need to compute value of this constant.
That t is a formal variable, and so the val t is the evaluation. Yeah, that's fine. Okay, thanks.
Yes, exactly. It's variable, or rather, it's even just a constant, and we code constants in some way. So let me also say what is important, what is not important in these conditions. For example, this last condition about induction is relatively weak. For example, let's imagine that we define truth predicate with a bounded formula using omega-1 function, or let's say omega-1 form. And if we do this in basis bounded arithmetic S2, then we would have induction for free for this formula and for bounded formulas using this definition. So in such a situation, induction is we easily get induction because we have the full bounded induction in a theory. But of course, satisfying the third condition is, I guess, rather much harder than satisfying induction in some arithmetical theories. So let me define this S12 of TR simply as basic axioms governing the rules of our function symbols. and equality, then polynomial induction for this weak class of formulas, and then and then the statement truth is a good truth predicate. So TR satisfies all these properties. So this is, of course, this polynomial induction is inside this truth. TR is a good delta zero truth predicate, and it can be easily shown that S2, so full bounded induction in the arithmetical language without truth predicate, is included in S1 to TR. So and intuitively, S12 captures P time, and S12 TR captures P time with TR as an oracle. So with a truth predicate as an oracle. But of course, there is a question how much of it our arithmetic knows, how much of complexity of TR our weak arithmetic can reconstruct. So now, okay, so PSPACE. So now, and I want to do first, I want to briefly say how we represent PSPACE, and then in the second part, I want to say how we prove witnessing theorem for this arithmetic. So, so representing PSPACE, it's more or less standard. We take a machine with explicit space bounds, so we know that a computation cannot take more tape than we prescribe for it. We assume that computations are deterministic, which is much easier to work with this assumption. And we assume that machine loops forever once it accepts. And the length of the input is just logarithm of W, more or less, plus minus 1. And let Tm of W be term with omega 1, which simply bounds any configuration which can occur during computation of M on the input W, because we take W as a sequence of zeros and ones. So the length of W is more or less logarithm of W, and the length of the computation and codes of possible configurations of M on W can be bounded by a term with omega 1. So we take such a term which can be computed from M simply. And then first let me write formulas which states that we can reach configuration C2 from C1 in 0 steps. Then there is a just arithmetical formula which states that we can reach configuration C2 from C1 in 1 step, and it is just arithmetical formula without TR for now. And then we can if we have formulas which expresses that let's say C2 is accessible from C1 in S steps, then we can write the same for S times 2 steps. And we, for let's say T is even, so we can, and S is just T divided by 2. So we can just use reach S just 1 times here, and we can quantify over intermediate configurations, more or less. So so we say that C2 is accessible in T steps from C1 if there exists intermediate configuration C such that either from C1 we can reach C in S steps, or not either, but we can reach from C1 C in S steps, and we can reach C from C2 also in S steps. So and I write it in such a form in order to have just one occurrence of reach S. And probably you've seen such formulas or such idea, for example, in Savage theorem on equality of non-deterministic p-space and deterministic p-space, because it's just this idea that we find intermediate step and we check the two condition. And here we do this using just one time the predicate reach S. And this is important because thanks to this, our formulas does not grow arbitrarily fast, I mean exponentially fast. The length of our formulas grows polynomially with the size of, with t, simply. So, or logarithm of t, indeed. So thanks to this, we can write short formulas which state that, so for that one configuration is accessible from another. Then we can do this, of course, with for odd t, but this observation at the bottom of this page is crucial, that we can write reach with in t steps by a formula which has length of 2 to the polynomial of logarithm of t. So this is a term which can be written with omega 1, with basis in basis arithmetic. So we have short formulas for that. And then when we want to express that one configuration is accessible by another one, what we do, we simply construct appropriate reached t, and then we put this formula under truth predicate. So now we use these formulas that we constructed just as a formula which we input to the truth predicate. And of course, we can write it equivalently as for all phi of such form, t are truth of phi. And this formula, reach of t, m, w, c1, c2, is our formula representing p-space computations, simply. So now t is a parameter. Before, t was a parameter in construction formula. So formula reach subscript t depended on t. And when we use truth predicate, this t becomes just a parameter, and we have one formula for that. So thanks to this, we can simply observe that in a standard model, such a form augmented with truth predicate for delta zero formulas, our reach expresses simply p-space computations. So semantically, it is a natural construction, and it expresses what we need, what we want. But of course, there is a question whether we can reconstruct this in a weak arithmetic. So, first question would be whether we can represent p-space. And probably it's quite tedious, but it can be proven more or less easily. But for example, we have uniqueness of computation. So for example, if d and d prime are reachable in t steps from configuration C, then d is equal d prime. Or we can also prove that for each C there exists, and for each t there exists a configuration d which is accessible in t steps, because our machines never stops. They loops when they enter accessible in accepting state. So we can also prove that for each t there is a configuration which is reachable in t steps. So everything like that is more or less easily proven. Concatenation of computation, splitting of computation in the middle, or not in the middle but somewhere. So so this can be proven, and so this is some basic properties. Then we can also prove what is more important, that indeed if our computation takes too long time, then some configurations have to repeat. So we know that if computation takes too long time, then we are in a loop, and either we already accept it or there is no accepting computation. So this can be also proven just by counting accessible states. and I think there is no need to go through details of this constructions, because they are fairly standard, and this is still a kind of bootstrapping. What is important is that we indeed, after that, we know that we can capture PSPACE in a sense that we can add function symbols for PSPACE computation to our weak arithmetic and defining axioms, and it will be a conservative extension. So from this first part, we want just this, that PSPACE is within reach of this theory. But indeed, what we want something more, because we want really witnessing function for this arithmetic. So not only we can capture PSPACE, but indeed we cannot prove totality of more functions of the form sigma b1 then they are in PSPACE. So we not only have the arithmetic which captures PSPACE, but its force, its semantical force, is not above PSPACE. So usually these arguments are given by cut elimination, and I avoid cut elimination. So we will do this witnessing theorem without cut elimination, but we go to another theory U12, and we borrow witnessing theorem in a sense from this theory. But so, and of course, weak upper bound for this PSPACE is given just that this sigma b1 formulas using TR in a standard model, they express it just PSPACE properties. But then if we want to do this upper bound in a theory, then firstly, we interpret our weak theory in U12, for which we have a witnessing theorem, and then we translate proofs of U12 into our arithmetic. So with this translation, of course, an obvious problem is that U12 is a second order theory. So the translation won't be kind of straightforward. And we just
Konrad,
yes?
can I just for a moment, because I'm quite ignorant about this whole area here. So did you say what a witnessing theorem is?
I will show a witnessing theorem maybe.
All right.
And let's do this in a moment. I mean,
okay.
Because for an upper bound, I mean for this second point, an interpretation, we do just a classical construction, and then I will say what is witnessing theorem. So first, interpretation. So I want to interpret our true predicate, and there is a standard notion of a set which evaluates a bounded formula. So let's say I want to have a set which witnesses that a given bounded sentence is true. So how this set can look like? So for each subformula of phi, I can add to this set for quantifier-free subformulas with parameters, with any parameters which is relevant for phi. So phi is bounded, so I can check for which numbers to which numbers phi refers, and I can check a bound on these numbers, and then for quantifier-free subformulas of phi, I can simply add to this set information which quantifier-free subformula is true and which is not. Then for example, for Boolean connectives, I can state, for example, that psi a bar 1 is in the set if and only if psi not psi a bar 0 is in the set. So psi is true if and only if, or maybe the other way around. Not psi is true if and only if psi is false, for example. And we can build in this set the a kind of set witnessing the truth of phi. So for quantifier, I can state that let's think for a moment that this Q is for all. So for all v less than t, gamma is true, if and only if for all substitution of parameter for v, gamma is true. And for all v less or equal t, gamma is false, if and only if there exists a parameter x such that when I substitute this x for v in gamma, then I got a false statement. A false in the sense of alpha, of course. And in the fourth condition, we add that alpha decides any bounded formula of interest simply. And so what is important is that such a set can be defined in this arithmetic U12. I will define it later. So we have indeed an interpretation of S12 TR because with the definition of TR, any other axiom of S12 TR is satisfied when we substitute this definition instead of TR. So then we have that any sentence provable in S12 TR is a PSPACE function because any sentence of the form for all there exists and then sigma B1 of TR because for U12 we have witnessing theorem. But okay, but I see that I should put this witnessing theorem earlier in the text indeed. So I'm sorry for that. So what we want to do this inside S12 with truth predicate. So we want to state that if I prove a sentence of the form for all and then sigma B1 sentence with truth predicate, then S12 TR, of course, with PSPACE symbol functions, can prove that this sentence is the truth of this sentence is witnessed by PSPACE function. So let me jump to show a variant of PSPACE of witnessing theorem. Okay, so this is a witnessing theorem we look for. So if an arithmetic U12 proves there exists phi such that there exists y such that phi of ay. So a is a parameter, y is a distinguished parameter, y is this exist y. So then we have a PSPACE function f such that U12 proves that phi of a and f of a, and with some additional parameters if there are some. So indeed, any existential quantifier which is proved to exist in this theory with such phi, not too complex phi, is witnessed by PSPACE function, and this is provable in our theory. So this is a classical form of witnessing theorem, and it is proved usually by cut elimination. So what we do first is usually we just do cut elimination for a theory, and then we say if a formula of a given form is provable, it is provable with a proof for which we have no complex cuts. And then from this proof, we can reconstruct PSPACE algorithm And for this PSPACE algorithm, our theory proves that it is a good witnessing function for there exists y. So this is a standard way of proving such things. And what I want to do, I want to prove such a theorem, witnessing theorem for S1 to TR, but without doing actually cut elimination, but with doing a kind of interplay between S1 to TR and this U12 theorem. So it will be we want to have so good correspondence, so good interpretations of proofs of this theory in our first order theory, that we can translate witnessing theorem from this theory to our theory. So but first let me so the strategy will be like that. First we translate proofs of U12, and then we used witnessing theorem for this theory. And but so what is our version? What is a version of U12 which I use? So we have second order sigma 1b1 formulas, and I said that it is strict if it is of the form there exists x, and this is just a sole existential second order quantifier, and then psi is just bounded first order formula. And we have sequent calculus which essentially uses just such strict formulas. So initial sequence are like that. We have comprehension axioms, but if I have phi which is first order, then I have a set Z which is a set of elements about which phi is true up to a term T. So this is bounded comprehension for first order formulas, but possibly with second order parameters. Then we have just standard rules for Boolean connectives, like here. We have introduction of second order, of course, first order quantifiers also, but interesting for us is second order quantifiers. So we have rules for introduction quantifiers on the left, on the right. So this is all just standard. Then we have replacement, and this is the place when Bass and Beckman differ from the classical formulation of U12, because they wanted replacement rule to be in such a form that there is only strict sigma 1b1 formula above and below the line. So if phi is just first order formula, then in the assumption for the replacement rule, we have just strict sigma b1, because it is there exists x such that phi, and below we have also just there exists y and then first order formula, and this y in a sense codes the truth. It is this y, it is a set which simply how to say, gathers all the phi for which I mean, here above we have for each a we have distinguished set xa, and y simply gathers all this x0, x1, x2, x3 up to t. So it simply collects all these witnessing sets which are above. And this is more or less intuitively what we should do to get such a y. Simply glue all this x for a equals 0, x1, x2. So if there is no question, I just leave this axiom. But important thing is that it uses only strict sigma b1 formulas. And then we have induction, which is also just for strict sigma 1b1 formulas, and cut rule, which is of no special interest for us indeed, because it's just the first order rule. And for such a system, we have cut elimination, and we have witnessing theorem. And then how we can use this theory to get what we want about S12 with truth predicate. So we need to translate sequence, but this sequence are sequence with second order formulas. They are of the form, so let me distinguish second order formulas with this sequence. So we have strict second order formulas in the antecedent. So there exists x1 psi1, there exists xk psk. And of course, we have such a strict second sigma b1 formulas in the antecedent. So in the, let's say, successor of a sequence on the right, there exists y1, there exists ym. So so I will interpret this second order variables as delta zero formulas. So here let alpha 1, alpha n it be bounded formulas which will correspond to this x1 x alpha 1, alpha n will correspond to second order parameters. So because we have some parameters which are not quantified, a1, an. Then b1, bk will correspond to this x1, xk. And then what with y1, ym? So then this y1, ym are on the right, so they need to be constructed. So, and we'll construct these witnesses for y1 and ym by means of delta zero formulas with second order parameters. So, it will be like that. If you give me delta zero formulas which you substitute for a1, an, second order parameters, and if you give me delta zero formulas b1, bk, which you substitute for x1, xk, witnesses for xy and xk, then gammas will compute witnesses for y1 and ym. But gammas, when we substitute in gammas alphas and betas for corresponding parameters and witnesses for quantifiers x1, xk. So, so this is the role of gamma, to compute witnesses for the quantifiers on the right of the sequence. And in this way, we get first order sequence when we removed second order quantifiers and we replaced second order variables by delta zero formulas. And it occurs that we have enough complexity to interpret proofs. So why this is so? Okay, so this is what I more or less stated that about this construction. And then, of course, sequence is interpreted as usually that a conjunction of formulas in the antecedent implies disjunction of all formulas on the right hand of the succedent of the sequence. And then, instead of cut elimination, we have a theorem that if we have a proof U12 proof of the sequence gamma arrows delta, and it is, you can assume that it is free-cut-free proof. So the only formulas in this proof are sigma 1 b1, strict sigma 1 b1. Then for each sequence in this proof, our sigma 1 2 of TR arithmetic proves something like that. There are gammas which compute witnesses for this existential quantifiers on the right. So no matter what formulas alphas and betas I substitute for parameters a bar and for witnesses for quantifiers on the left, gammas will produce me witnesses for the existential quantifiers on the right. And what is important is that gammas does not know what alphas will be given and what betas it will be given. So it is a kind of delta zero formulas here. These gamma formulas need to have some quite a strong computational strength, because it should work for any alphas and any betas. And we assume only that it is provable. It was proven in UW2. So we have this form of witnessing theorem, and the proof of this is more or less standard. So for example, for comprehensions axiom, if we have such an axiom, then we can witness Z just by taking a formula which is gamma, which is simply A. Maybe I go to another slide. No. So if gamma is just A, oh no, it is no. Excuse me. If gamma is just this phi, then it witnesses the truth of that there exists Z such that this property holds. I mean, and this right is a bit more complicated because there is one technical obstacle, namely the formulas which we can use under our truth predicates are just Peano formulas, bounded Peano formulas. So, and this phi is in the language of basis arithmetic. So we need to translate any notion from basis arithmetic, like the logarithm function, or most importantly, omega-1 function, into language of Peano arithmetic. But this can be done. So once we do this, indeed, essentially, it's simply like that this phi, which is bounded, and it can be made bounded in the sense of Peano arithmetic, simply witnesses this exists Z quantifier simply. So, for example, this axiom is quite easily satisfied. Then, if you have such an axiom, we also do not need to do a lot. Simply, if we have this A and we have truth for phi of A, then we can witness there exists Y just by this A. So gamma may be just A of X, and even more if A does not occur in the lower sequence, we are just free to take any formulas indeed. And what is interesting, replacement maybe is not also so interesting, but induction is interesting. So let me tell a bit about induction. So induction has a form like here. If I prove from phi of A plus 1, then from phi of 0, I can prove phi of logarithm of t. So this is linked induction, which is known to be equivalent to polynomial induction. And what does it mean? Here in the slide, here below, there is this translation, which I want to skip. So for a moment, let's think about this, that phi is just there exists Y such that psi, and think of this psi prime like just psi simply. So our translation of the upper sequence gives us something like that. If that I have a formula gamma Y with such a property, if psi of beta of X, where beta is a delta zero formula, is true about X, then psi with gamma Y with beta of X, beta X substituted for X in gamma Y is true about X plus 1. So from witness for psi and X, gamma Y produces witness for psi and x plus 1. So this is just what we have from the upper sequence. And what we want a formula gamma, let's say logarithm of t, such that from the witness for the truth of beta x and 0, it produces witness for logarithm of t. So an obvious way to do this is it would be to iterate gamma of y, of course, because if psi is true about beta x 0, then gamma y of beta of x substituted for x is true about 1. And then when we substitute this formula again into gamma 1, we have a witness for 2, and so on and so on. So this is a kind of obvious construction. And let's do this construction. And then we prove more or less by logarithmic induction that indeed such constructed gamma is a good witness for existential quantifier on the right. So provided that psi is true about beta of x and 0, then psi of this logarithm of t repeated substitution starting from beta of x is true about logarithm of t. And of course, the problem is that this works only when our formula gamma y of x has only one occurrence of x, because otherwise our formulas may grow exponentially, the length of the formulas, and we can go outside of the model constructing these formulas. And of course, we see in this example that our formulas may be non-standard. So our witnessing delta 0 formulas may be non-standard, and we really need to substitute them into truth predicate to speak about the truth value. So if gamma of y has only one occurrence of x, then we can go with such a construction and it will be fine. And the general case, when we have more occurrences of x in gamma, may be solved just using a standard technique by Ferrante and Rakov and by Solovey. But we can translate gamma into an equivalent formula with only one occurrence of x. And then we just use this equivalent formula. But of course, we need to do this within a theory because our formula gamma y of x may be already non-standard. So we need to translate it within a theory, and then we can repeat the construction. So when we do this, we have in a result, we have something like that. But if I have exist y such that psi first order, and it is provable in S1 to TR, then sorry, this is our aim. We do not have this now because we only translated proofs of second order theory U1, 2. And this is what we want to do. And the translation itself does not give us already this, but we need to make something more. So proof strategy for the witnessing theorem will be like that. We assume that S1 2 TR proves there exists y such that psi. Then we jump to U1 2 and we observe that it proves there exists y such that psi, where this big psi is just an omega interpretation of truth predicate that I talked before. Then we use witnessing theorem to get a PSPACE function witnessing this exists y. Then we translate back to S1 2 TR. But what we know that we can translate back, it's something when this when we do not have we do not know what is the relation between this psi and the truth predicate of S1 2 TR, and we need somehow bound this psi with truth predicate. And we do this using finite approximations of the truth predicate, and we somehow state that these finite approximations are good enough. So how we do this? So first, if we have such a formula provable in U12, then by our translating of proofs, such a formula is provable in S12TR. There exists gamma, for this initial exists X, and then for all alpha 1, alpha n, delta 0, which replace parameters, second order parameters, and then psi of TR of gamma, and so on and so on. And here all second order variables just vanished and are replaced with TR of gamma, TR of alpha I. Then, so in particular, this psi interpreting TR is also non-existing in the translation here. So what we use now? We axiomatize that P is a good truth predicate. So we just expresses these arithmetical sentences which I formulated about truth predicate. We do not need to express induction because we have induction for free in our this amount of induction we have for free in our theories. So we need to state it explicitly that P satisfies this amount of induction. And then there is a result of by Putlag that we have predicates TR subscript n, which indeed approximate truth predicate for delta 0 formulas. And I will jump to another slide because it states in a theory what we need. So these predicates are of polynomial sides of n. Then our theory S12TR proves that indeed they satisfy all the properties of a good truth predicate. And moreover, this third point is a kind of is-knowing lemma that TR of this finite approximation truth predicate of phi is just equivalent to TR of phi. So these partial truth predicates are as good that we can get rid of them under TR. Or in other words, TR knows that they are good truth predicate. And then with these predicates, we can prove witnessing theorem. So this is again a witnessing theorem, so that if we prove exist y such that psi in S12TR and psi is just sigma B1 formula with TR, the predicate TR, then we have PSPACE machine P such that P computes witnesses probably in S12 with truth predicate. So, and now how we do this? So, assume that S12 proofs exist y such that psi. Then, of course, U12 proves there exist y such that psi and big psi as interpretation of truth predicate. Then let term T of A be term bounding all relevant elements in psi of TRA and P of A. So so then we can end bounding computation of P of A. So indeed, U12 proves that P of A is less than T of A and psi of big psi A and P of A. And of course, since big psi is an interpretation of truth predicate, we can write it in such a way that big psi satisfies properties of a good truth predicate, probably in U12. And because we wrote big psi in kind of standard way, then it is easy to show that it satisfies these properties up to given T of A, and for formulas of length logarithm of T of A. And when we have this, so we can also show that any two sets which are good truth predicates must agree on this formula. I mean, if I have one set which computes truth for delta zero sentences up to a given point and another set, then they have to agree on this true if I have a small amount of induction. So what U12 really proves is that either set R is not a good truth predicate, or set R witnesses that psi of R, A, and P of A. So, and when we have this, we may jump back to our first order theory with truth predicate. Because what we do, we simply translate this last formula, we translate this formula using our translation of sequence. So we know that S12 with truth predicate proves for all gamma delta zero, either this gamma is not good truth predicate or psi of TR of gamma A and PA. So this is just a translation of what we just proved in U12. And this translation is given by translations of proofs of U12 into S12 TR. So then it is for all gamma, and now we need gammas which approximate truth in a good way, and we know that we have such gammas. So because of that, we simply, for this gamma, we take these finite approximations of truth predicate. And since for all gammas, then also for these approximations. And now we know that either these finite approximations are not good truth predicates, or psi of TR of this TR of TA, A and PA. And by the lemma, which I called it's knowing, we can replace this. Instead of writing TR of TA, we can just write TR simply in all these places. So we get rid of these finite approximations and we just use TR in this formula. And when we have this, we see, okay, but TR is a good truth predicate. So, so the first disjunct is simply false. And we got simply that S12 TR proves psi of TRA and P of A. So we got witnessing theorem for S12 with truth predicate by this translation again. So so instead of using cut elimination, we somehow showed that this theory is on the one hand weak enough to be interpreted in U12, and on the other hand, it is strong enough to interpret enough from this theory, and also to approximate truth predicate to that point that we can use all of this to prove witnessing theorem. So this is a witnessing theorem. And now, so what we know first, let me observe that when we write a natural definition of a truth predicate, then it is usually good, or always good. I mean, when you write truth predicate for delta zero formulas, it satisfies these properties. And if our base arithmetic satisfies enough induction, then it satisfies also induction. And so, for example, if in S2 with omega-1 function, we could get a truth definition for delta zero sentences with just constant and variables as bounds, then we would get PSPACE included in polynomial time hierarchy, probably in this arithmetic. And that the question about truth definition for delta zero is more about PSPACE, representing PSPACE, than exponentiation function. And of course, one can ask different various questions about this. And maybe the most interesting would be if I have some, what are model theoretic properties of such theory? For example, what kind of end extensions of models of such a theory we can get? Because instead of using X, we can use truth predicate with some natural properties, and then what end extension of a given model of such a theory can be defined, and of course some variations of that. Okay, so and we can, for example, we can base arithmetical theory to check whether still we can have a witnessing, we can capture PSPACE and have a witnessing function, and okay, and some other properties. Okay, we may. Okay, so thank you. That's all I wanted to say. Sorry for talking so long, indeed.
Thank you, Konrad. It was a lot to digest, even in this hour and 15 minutes, but it's interesting. Are there any questions? I have, okay, but I have one, because this is not really something that I know much about, but this last item for your future work, model theoretic properties. So I have never seen axiomatic theories when instead of some variants of fast-growing this or that function or exponentiation or sub-exponentiation, you have some assumptions on the conclusions. And so has there been similar work for other theories that would be similar to this S1 to TR, where there would be some interesting results to look at?
So it seems for me that at least if we consider truth predicate for bounded formulas, then I'm not aware of a work which would be more or less in this line. But at least if reconstructing what can be get from a truth predicate within a theory. Mm-hmm. Of course, I mean, there are classical constructions we just use truth predicates or some variants of truth predicates. So one can mention, for example, even this old famous paper by Wilkie and Paris from Moscow, when one of conditions under which they proved that there exists an extension was a kind of existence of a truth predicate. Mm-hmm. But it was rather model theoretical approach and not theoretic, not within a theory, I would say. And other works like satisfaction classes, it's also either for stronger class of formulas or and not induction, for example. Or stronger class of formulas and some kind of induction like Cieśliński and others.
Okay. So if there are no questions, then let's thank Konrad. Thank you, Konrad, very much. And as I said, we'll resume our activities sometime late January or early February. Okay, thank you.